Hi guys, long time no see. Welcome to the next video in the Stage Functional Programming in Spiral series. For the past few months I had some pretty heavy repetitive strain injury, and as a result I had to stop making the videos. I couldn't even program properly, let alone do screencasting. I'm still not over it. In fact, it's probably going to take another few months at least. I've gotten a bit better. I've learned some exercises for the hand, to stretch my fingers like this. And this really helps, but it still doesn't mean I can program as I used to. But just for this particular part, I really wanted to do a video, because it's going to be so good. In this video we'll be covering matrix multiplication in Cuda. Now you might be wondering, why do we need to do matrix multiplication? In fact, this isn't my first choice. My first choice would be to get matrix multiplication from some library like this one. On paper, cuTLASS looks pretty good, but I looked into it. I studied it for like 5 days, and if I wanted to make a device kernel that runs only on the GPU and doesn't really do any calling from host, it would be very difficult. I've actually gone ahead and asked the author for maybe an example of how this could be done, but I didn't have any luck with it. What I want to do is make a poker game that runs entirely on the GPU, as well as the machine learning library that runs entirely on the GPU. What I had in mind is something that you see on this diagram. At the start of the kernel, we'd have a subset of threads just running the poker game loop. This will go through the poker game, and on every street, like preflop, flop, turn and river, on every betting street as well, there will be action selection, and this would call out to the machine learning model, which is a part of the machine learning library, and this would get the action. And for this only a subset of threads would work. For the poker game loop, I mean. The rest of the threads would have would go past the game loop and go into the neural network model loop for the machine learning library. And all the threads would eventually meet at the device-wide barrier, or the grid-wide barrier to be more exact. And this would run the code in a synchronous fashion. While the poker game itself, all the threads will do individual work. So you can imagine it, for example, if you have something like 10,000 threads, maybe 500 threads would be responsible for actually running the game, and the rest of the time the other threads would wait at the neural network model loop, essentially doing nothing. And when all these action selections have been made, they'd meet at the device-wide barrier and go and run the neural network model to get the action probabilities. So for the neural network model, for the machine learning library, we need the matrix multiply as the very first thing. We need to do a reality check. I did the no-limit poker game as well as a neural network model back in 2021. It was done on using Python for the game, and the neural network model was done using the PyTorch library. I had a bunch of models that I was trying out back then, and in terms of performance I got something like between 10,000 and 100,000 hands per second. For this particular library I want something like 100 million. Otherwise I'm pretty much wasting my time doing this. So for this part of the series, we just need to do a reality check. You know, if you have something like a very simple linear model that runs entirely on the GPU as well as the game, we should be able to get something much better than what we would get if we were moving data back to host and back on a, you know, for every action selection. And I personally don't know. I have no idea what kind of performance I could expect. If we cannot exceed, you know, something we'd get on the host by 100x, there is no point in doing any further work. We should just, you know, sit back and maybe wait until a couple of generations of hardware has passed before trying this again. So yeah, you know, when I did this using PyTorch, the PyTorch already had a matrix multiply in its library. In fact, we already have that through the cuPy library. It's very easy to use. This is basically the spiral code that generates the matrix multiplication calls on the Python side. If we compile this, for example, okay, I won't compile it right now, but just take my word for it that this does a matrix multiplication on the just using Python, and you can do this with PyTorch. But if we wanted to do all of this on the device, it would be a lot harder. And as I said, I went through back and forth with the author, asking for the example, but you know, the author is very busy and couldn't provide it. You know, so you know, I'm getting some advice here, and it basically boils down to me having to go through this very complicated C++, the template library that's made using templates. It's the code is pretty nasty, and I don't want to waste my time doing that. So as it happens, cuBLASDx came out recently, and as you can see, the cuBLAS library preview is a device-side API extension for performing BLAS calculation inside the Cuda kernels. By fusing numerical operations, you can decrease latency and further improve the performance of your applications. This is basically what it says here, and this is exactly what we need. In the past 2 days, I gave it a try. It's actually a part of the mma.h package, you know, and okay, I went for it. I accepted the license agreement, and when you do that, the first thing I saw was this, Linux x86. And so that's our first obstacle. That's the library is Linux only. Actually, you know, it's a C++ header library. I thought that, you know, maybe it could work on Windows. I gave it a try, and it turns out that I got an error that it cannot compile using MSVC, which is the Microsoft Visual Studio C++ compiler. So that's a bust. The next thing I tried is actually getting this and using it in Linux through the Windows subsystem for Linux. And that's Windows VSL. The Windows subsystem for Linux allows you to have a Linux installation, to run a Linux distribution directly from Windows. So I got this. It's pretty easy to actually install. There are Cuda specific instructions. You basically have to have a Cuda driver, then you run this. Then you also need to install the Cuda toolkit. Even if you have it on Windows, you need the Cuda toolkit for VSL. Okay, and I installed all of that. I installed a bunch of Python packages to try to get this to work. And what happened is that I got an error when I tried to compile the simplest possible program. I got an error when I tried to compile this, and as you can see here, it's basically doing nothing in this global function. The only thing I have included is this cuBLASDx HPP header, which is necessary. And when I do that, I get some kind of weird error that no instance for overloaded function matches the specified tab, blah 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 blah. Anyway, so the cuBLASDx is in preview. It came out like 2 weeks ago, and it doesn't work on Windows, and apparently it doesn't work on Linux either. Maybe it will start. These bugs will get fixed in like a few months, who knows, few weeks. But until then, we're going to have to do our own matrix multiplication, even though this is not really the path that I'd usually want to take. You know, it's 2025, you would expect that you would be able to find matrix multiplication in a library somewhere. I mean, there are like 2 of them, but cuTLASS is too complicated. You know, when you study a library for like 5 days and you cannot get off the ground, it's time to drop it. And this one doesn't work. But I have to admit, cuBLASDx has a pretty good, you know, interface. And it's really a pity that, you know, it doesn't work. Like this is very easy to understand compared to what you see in cuTLASS. In cuTLASS, it exposes all kinds of low-level details that I wouldn't want to care about directly in the template. Anyway, what we have to do, we won't be doing matrix multiplication all from scratch, of course. What I'm showing you here on the screen are the Cuda samples. This is like the Cuda sample code that NVIDIA provides with the Cuda toolkit. And there are actually plenty of them. And amongst them, there are samples which do various kinds of things. There are sorting, but of course there's also general matrix multiplies. And you can see this SLN, ViViX project. These are actually Visual Studio project files. So you could, if you wanted to, run these examples on Windows. And what happens when we go into this? We'll see that you know, there are a bunch of globals. I mean, this is not good. We want to be able to specify our own matrix sizes. So that's one of the reasons why we had to rewrite all of this in Spiral. The other reason, and the main reason why I'm doing this as a video instead of, you know, doing it in private on my own, even though it's harder. If you look into this, this is an example of a general matrix multiply kernel. And take a look at this shit. You'll see that everywhere. This, you know, this at first glance, this kernel seems very complicated. For example, take a look at this. Since all this pointer arithmetic seems very hard to deal with, and in fact it is. I iterate this code as pretty bad, but this is more a problem of the tools that the authors were using, which is C++ in this case. Because C++ doesn't have a proper tensor class like Spiral does, they had to do all the pointer manipulation and offset calculations manually, which is why this came out so badly. And the main reason why I wanted to do this in spiral, why I wanted to rewrite all of this in spiral, is because it would come out much cleaner. So it's going to be a treat to really show how spiral can abstract all of these into maybe 1/10 of the code you see here. And let's get started. In contrast to the past videos, I won't be, typing in in a text box that's, in the top right corner, because it would be too strenuous on my hand. So instead, I'm going to have to put pauses in between the coding sessions and narrate myself as to what is going on. Okay, we have our spiral project here. The tensor class is in fact, mostly done. But to start things off, we're going to have to make some functions that will be very helpful for us later. As you can see, this tensor is very similar to an inverse array that I think we've covered in the past, but the individual elements have this offset field. They also have the strides, which have the same type as the dimension. And why this is necessary, and the additional functionality it provides us compared to inverse arrays, is that we can now have multiple dimensions, and we can also take the views of them. For example, if we have something like a 1000 by 1000 tensor, we can take the view that looks into, the 400 to the 600 dimension for both dimensions. And in fact, this view is, you can see it being implemented here. It takes the slice of the tensor view, and this can go. This works for an arbitrary number of dimensions. We can split them, we can flatten them, we can apply them from left to right, similarly to a function. The type of this is actually pretty informative. You have this tensor AB, and it returns a tensor B, meaning it indexes into the first dimension of the tensor. The split function is particularly useful because you can pass in a list of sizes, and it will split the tensor into those specific sizes across a particular dimension. And anyway, to start our session off, this function you're looking at here is actually its finished form. And we'll start things off by implementing it from scratch before moving on to working on the matrix multiplication proper. For now, just enjoy some Toho music, and we'll be back in 16 minutes. I mean, my voice will be back. Okay, we're back. What we're going to do from here on out is get started working on the examples. What we've done is created some extra functionality in the tensor class so that we can split the tensors. That is, reshape them. Previously, we had that capability, but it would have required the whole tensor to be contiguous. That is, for the first dimension to start with a stride of 1. And since we are mostly going to be dealing with views, that's not a very good thing to have. So instead, what we are doing now is getting the last stride and passing that as the first argument to the tensor extend. Sorry, I meant to assert stride contiguous. We had this functionality before, but we've modified it so that instead of the initial value being 1, it's getting the last from the stride, and that's a big boost in usability for this function. The way the whole thing is implemented right now in terms of flatten first and reshape first is quite clever, and I like it. We're just making use of reordering to do the reshaping for the second dimension. And for the entire dimension, we just add an unit. Reshape the first and then take off that unit value. If you look at what the type getting passed in, you'll see that it's just a unit. Okay, now what we are going to do, as I said, we'll get started on the examples. And what we will need that reshape for is to split this big matrix. In the examples, they're using 512 by 512 matrix, and we'll be splitting it up into smaller tiles. The examples in particular split it up into tiles of 128 times 128. So that's about dividing this matrix into each dimension of this matrix by 4. So we'd get something like the following. First, we'll reshape the matrix to something like this. It's important to do it like this, so the dimensions are split along the right axis. Then we'll do a reorder to turn it into something like this. And why this is important is because it will allow the blocks to iterate over the outermost dimension. It will make applying the indices much easier. And this is just for the blocks. We'll also need to split this entire matrix again. And because we've reordered the dimensions, we moved this 4 here, 2 places to the left. And as a result, this dimension and these dimensions are now non-contiguous. So that's why we needed that particular split. Inside the block, the warp matrix multiply instructions actually work on 16 by 16 tiles. They can also work on 8 by 32 and 32 by 8 tiles, at least for the float 32 data types. So we also need to split this once more, and that's why we needed those new reshape functions. It's going to take some work. We'll have to use reshape along with reordering to get this 128 into the last or the first position, but we'll split that into 8 tiles each as well. Then we'll push these inner dimensions to the outside. And this will make the entire thing a lot easier to deal with, because this particular tile will get loaded directly by the WMMA instructions, warp, matrix, multiply, add instructions that the newer generations of GPUs have. This will get iterated by the warps, and this will get iterated by the blocks. And in fact, what we could do, and what we should do, is actually group these dimensions and iterate over them directly. So that's what's going to be the plan for our first example. The Cuda sample that I showed you yesterday, I mean half an hour ago for you, that would be this sample. In fact, doesn't have just a single example or a single kernel. It in fact has 3. This one computes a gemm using shared memory, but it doesn't do asynchronous loads. Instead, it just uses regular ones. Let's see. Where is the second one? Oh, this is a simpler one. This one actually doesn't use any shared memory at all. Instead, it loads them directly from the global memory. And this is what we're going to use as our initial example before moving on to the ones that use shared memory. But where is the third one? I know there was a third one in here somewhere. Just a sec. Okay, I found it. It's actually in a completely different example. This one uses the brainy float data type, which is a 16-bit float. And it has an async copy version. The one that I showed you earlier, in fact, that doesn't. But I looked over the examples and they're pretty similar. So once we do it for the float 32, it won't be much work to change it, so it supports 16-bit floats. For now, let's start with this one. One thing that I've changed my mind is using cuBLASDx. It leaves a sour taste in my mouth to just leave it aside, because even though the library is complicated, it's a lot of work went into it, and it could be useful if we could get it to work. But starting off at the device kernel level, I mean at the kernel API level, is too much. So after we've done all these examples, after we've translated them to Spiral, we'll start bringing in the library, and we'll convert the operations so they use the cuBLASDx functionality, starting with the warp. And after that, we'll slowly make our way upwards towards the kernel API level. And let's get started. It's time to do some programming. That was a pretty tiring session, but I am satisfied with the end result. Let me do a little tour of what we've done so far. At the start of the kernel, we create a grid, then we split it into tiles that are conveniently warp-sized. And then we pass in the tensors from the outside. In contrast to how it's done in C++, where you have to pass in raw pointers, in Spiral you have the tensors as an arguments in the host. They'll be bound to some variable, and you can just directly drag them in through the lambda. Lexical scope is really great. And they'll automatically get passed into the kernel as separately as pointers and the offsets and the strides and the dimensions. And inside the kernel we have this we are doing this reshaping that I alluded to in the previous explanation. The tensors are two-dimensional. In particular, the tensor A has the m and k dimensions, and then we split them up into separate pieces. It's important to do it like this, because otherwise, for example, if we maybe switched around this part, the splitting would have worked, but the order of the dimensions would ended up being incorrect. So it's important to follow this. And this reorder function doesn't actually do any splitting at all. It just takes the individual dimensions and moves them around. And that means that the strides between the dimensions, when they're first reshaped, they'll be in ascending, starting with with 1 for the innermost dimension, and then increasing linearly, monotonically, as it goes outward. But when we do this, these two dimensions, for example, kfrag and mfrag, won't be continuous anymore. Anyway, we do this for all the three tensors. C is the input tensor. B happens in the example to be column major. And what these layout parameters are doing for the fragments is controlling the transpose. And in fact, if we wanted to, we don't necessarily need to do this reshaping inside the Cuda kernel. We could very easily just drag them out like this, and then do the reshaping outside the kernel. But I'm not really sure which one is better. Right now, all the tensor sizes, as well as the strides, strides and tensor dimensions are known at compile time, so it doesn't really matter either way. But if they weren't, this would result in a lot more variables needing to be passed into the kernel itself. So maybe it's more memory efficient, I don't know, to do it inside. Maybe it would give the compiler more opportunity for optimization. And this part is really nice. For example, if I hover over this is the C tensor, we see that we have the outermost dimensions m and n, and they're only applied inside this particular loop. And what this loop is doing is iterating over the m and n dimensions. And if we remember to what we were doing much earlier, and in fact, let me just explain it right now. The tensors can have, the tensor module has this apply function, and this type is, let me show you. Where is the tensor? I put it in core base. Maybe I should move the function somewhere else instead of letting them be in type. Never mind that for now. excuse me. Yeah, here's the apply template, and you can see the type here. We pass in the index. This is the A type, the first argument to apply. Then we pass in the tensor, which has at least 2 dimensions, A and B. And then what we get out is the tensor with just the second dimension, meaning it kind of applies the first dimension. What this really does is simply increments the offset field for the tensor. If you look at how the tensor is structured, it has the tensor bodies. It also has this dimension field. And this dim is the actual dimension. So it could be, for example, for the tensor that we are looking into is 512 by 512. And the tensor bodies, those are the individual elements of the tensor. They are actually arrays. And they are accompanied by the stride and the offset. The stride is it starts at 1 for the innermost dimension, and every outer dimension is the product of all the previous dimensions. And if the tensor is whole, then these tensors are contiguous. But if you take a slice of a tensor somewhere, then this stride will become non-contiguous. And the reason why it has the stride and the offset is so that the tensor can be zipped with other tensors that are views or non-contiguous. And this makes it a bit more functional. Anyway, yeah, this is the zip function. You can zip arbitrary tensors as long as they have the same dimensions. Going back to our matrix multiplication, we just apply the outermost dimensions for the A, B, and C tensors inside the loop. And what we get, A and B have this K dimension in the outermost level. So we need to iterate over it using the individual tiles. First, we initialize this accumulator fragment, we set it to 0, then we do a linear loop. This is basically a perfectly ordinary loop. It just has, instead of only being able to take in regular integer indices like the loops in the loop module, that is these loops here. These are the regular loops, and their dimensions need to be integers, not just numbers, but integers. But for this thing here, they actually can take an arbitrary number of dimensions with an arbitrary number of elements. In this case here, note that we are not really taking an integer index, but a record which has an integer field. In this case, the record is actually k. It's something like an object, like whoops. It can be something like this. It's a spiral record with an integer. And in the future, I think we might want to iterate over not just a single dimension, but two of them, like for this loop tile here. It's a lot easier to iterate over two dimensions that have to iterate over them one by one. Okay, and inside this loop linear, we iterate over the outermost dimension, which is in this case k. The reason why I'm using records instead of bare integers like I attempted to do initially, because like this it's a lot harder to make a mistake. When you have something like 4 integers back to back, it's very easy to, you know, mistake one of them for another. But when I hover over this like so, I can plainly see, oh, here is the m, here is the k. They are at the outermost level. And it's very hard to make a mistake like this. Contrast that to, for example, the C version of this code. Here, you can see that they're doing arithmetic for calculating the correct offset. Whereas in the spiral version, all of this is being done automatically. Maybe if you look at this example in isolation and study it for a while, this manual calculation might not seem so bad, but you have to understand that when we start loading from shared memory, there'll be even more dimensions at the outermost level. So things will just get more complex and complex. And in this example, the leading dimension here doesn't even support padding, while in the spiral version it does. It also supports the tensor views. Excuse me. All of this is done automatically. We can, if in the spiral version, if we got for example, the tensor dimensions wrong, or the wrong way around, or there is some kind of another error, we have asserts right there in the loading functions that will warn us about it. But over here, if you go over the tensor bounds, or in this case the one-dimensional array, you won't get anything. You will have to scratch your head and really think about it, what is going wrong. Maybe do a bunch of prints to debug it. And this is very strict for a code. I mean, it's nothing too fancy. We just reshape the tensors, we do a loop over them, we apply the outermost dimensions, then in the innermost loop, we load the fragments, and we do the matrix multiplication here on the individual fragments. We accumulate them in the accumulator fragment, and then we load the C fragment from global memory right here on line 151. And what we do here is simply iterate over all the fragment elements. So we can do this this bit of arithmetic. We scale all the elements of the accumulator by alpha and then add them to the elements of the C fragment, which is being multiplied by beta. Then we set them to the C fragment. Then at the end of it, we store the C fragment to the C tensor. And it's very nice like this, because we have this tensor, we have the fragment. We aren't dealing with row pointers, so it's impossible to pass in the wrong thing by accident. And if you wanted to really beat the C version of the code, this is how you do it. What we have to do next is actually to test this out, because most likely there are some errors. I did a lot of programming. I did pretty much this entire these two modules entirely from scratch. Excuse me. It was really quite difficult to do these index projection functions. It's easy to get confused at what is going on, but I factored them out really nicely. But I can't be 100% sure that everything is right. So we'll have to test it out. We'll also have to do this. We'll also have to do the dimensionality checking, so that the individual dimensions of the A and the B tensor have the correct dimensions. Also, in addition to that, one thing that I'm going to a bit diverge from the original example is add support for transposition, because it's a very, matrix multiplication has to have the ability to transpose the individual arguments That goes for both the two inputs as well as the output. Just for the sake of testing, we'll move this out into the host. I mean, the reason why I'm doing these examples is so I can use matrix multiplication directly inside the kernel for the machine learning library, which we'll work on in the future. But for now, it's actually easier if we get an exception directly in the host code instead of the Cuda kernel. So we'll put them here. We'll move them back in later. Now, do we have anything we need to do before we start? Yeah, we'll also have to calculate. We'll also have to calculate the correct occupancy. I put in this thing for 24 grids, and we could go a lot further. I mean, one block per streaming multiprocessor is not that much. We could probably go for 6, which might end up being too much. So I did a little bit of in the C++ version. Cuda has a function to calculate the occupancy directly, but I reverse engineered it thanks to Bing and implemented this function. We'll just import this Python thing directly into the code and then make use of it in order to calculate the correct number of blocks per SM. No. Yeah, we'll start work on it. Before we move on to the next example, we'll play around and try to get the transposition to work correctly. And once we do that, we'll have everything we need to do the next example. It will be a very straightforward upgrade from what we have here. The only thing we'll be adding is loading from shared memory. We'll split these outermost dimensions another layer, another time, and then we'll iterate them using the individual blocks to load the data into shared memory before loading them into the fragments. Over here we are just loading the fragments directly from global memory, which isn't the best thing to do. But it's actually a lot better than how it would be in the previous versions of GPUs. For example, in my old GPU, they wouldn't have this warp matrix multiply add instructions. Instead, we'd have to use the individual Cuda cores to do the floating point arithmetic needed for the matrix multiply. And the reason why that is bad is because matrix multiplication is a cubed time algorithm. So for example, if we load each element in the A fragment would be loaded maybe 512 times, which is the size of the opposite dimension. Here, since we have the fragments, it would only be loaded like 32 times. So it's like a maybe it's a 16 times improvement. But if we use the shared memory, which is like something like the 15 times faster than global memory, we can use that. We can use it to amortize those costs. Shared memory is designed so each load and store only take a single clock cycle. We'll get started pretty soon. The next thing to do is to do the testing. Then we'll do the transposition. Make that 3.5. I finally figured it out. It turns out when you compile this kernel with NVRTC, it works correctly. It works pretty fast too. NVRTC is NVIDIA's runtime compiler. Compared to NVCC, which is the NVIDIA regular compiler, it doesn't compile host code like NVCC does, but it does compile device code. And this allows us to get around that particular bug. Now that we've gone through this blocker, we'll be able to resume making progress. If you look at this, it's actually pretty fast, quite a bit faster than NVCC. And since we're only compiling device code, the reason why I didn't go with NVRTC from the start is because for the longest time it didn't have good library support. For example, the Cuda Unbound library, which has various sorting functions, scans and reduces. Back in 2018, it wasn't supported. That was when I did serious GPU programming last time. But it's 2024, and since then things have changed. For example, Cube got some rudimentary NVRTC support, so we could use that. And since this particular error that we ran into was the same one as for the cuBLASDx library, we'll be able to use NVRTC to compile it in the future. I thought that we'd need to wait until it gets better supported, but the bug didn't have anything to do with NVIDIA's compiler. It's all CuPy's fault. This thing here. And as it turns out, cuBLASDx does have support for NVRTC. And I think with this, since we're only compiling GPU code, it doesn't really make sense for it to be, for example, dependent on the OS. I think if we focus on the NVRTC backend, it should work on both Windows and Linux. And that's a very good thing. We'll be able to use this library to make very performant kernels that use shared memory. We'll get to it later, after we translate the shared memory example on the main Cuda page. For now, let's get back to testing.